Okay, most of y'all turned in 11 and did pretty good on that. Is there any questions before I move on? Okay. Going to go over chapter 12 today, and I already put the homework up. And then I'll do an online, I think I'll do an online for 13 on Thursday. 13 is a very short chapter, so I don't think it'll involve too much. Then we'll have next Tuesday to go over any other, no, Tuesday we won't be here. After we finish 13, we'll have another test. So I'll have to decide. We'll see how Thursday goes, whether we have it Tuesday online or some other time. Anyway, right now let's do chapter 12. Chapter 12 is about stresses and beams and how to design for them. Where's my little pencil? So we're starting to use the formulas and stuff that we've gotten to figure out how to design a proper beam. As we learned in chapter 5, the beam supports a transverse load intended to produce bending. So beams will tend to bend like that. So now we have to investigate the bending in the resisting moment to design our beam. We have to understand all of these different things, how it bends, and what the stresses are to design the beam. The resisting moment is the action within the beam that resists the bending. So that's on this picture here. You can see, and this picture's in the textbooks too. It talks about, this action, and that's resisting the beam twisting and bending. The fibers in the upper part are in compression. That's what the C means right here. So all of these fibers, when above on this side, are all in compression, and then down here they're going to all be in tension on the bottom part. That's what the T means, and those act against each other when the beam bends to keep it stiff. The horizontal plane separating them is the neutral surface right here. So this is a cross section through the beam, and this is looking sideways. So you got your neutral surface. You've got compressive forces and tension forces. So all of this stuff is going on at once. And remember, back from a while back in the semester, the sum of all the moments must be 0. So it's all going back to those basic truths about stability in beams. So the sum of the moments in the compression and the sum of the moments in tension are equal to the reaction of the external force on the beam. So the sum of all these compressive moments and the sum of all these tension moments is going to be equal to the reaction of the external force on the beam, which will be that. So this is going to be equal to all of that. So this theory, the bending moment equals the resisting moment, and that's called the theory of flexure, which it talks about in the book. This can be expressed in a simple formula. It goes through how to get all that. I find that pretty boring. But the theory of flexure basically is M equals Fs, which is an expression for the resisting moment involving the size and shape of the beam, the cross section right here, this piece right here, and the S, the cross section, which is the section modulus, and the material, which is represented by F, it gives you a detailed explanation in the book, but like I said, y'all need to read through it, but I'm not going to go through that right here of why that formula works. So with all the formulas they give you and the charts and the tables, you plug it into the design to design your beams. I think it's simpler than what they make it out to be. It is important to remember that the flexure formula, though, can only be used for homogeneous beams, meaning one material, like wood or steel. You can't do it on a concrete beam with steel reinforcing or wood with steel in it. It can only be used on a homogeneous beam. So after you check for the moments, then you got to check for shear. Make sure your beam is designed for shear as well, and we'll go over this. So let me go down a little bit. There. So for any particular cross section, you have remember what I is? The capital I. Remember what that stands for? You have both I and C, where those are the geometric qualities and quantities that are constants in any cross section of a beam. So if you have a beam, we'll just use a simple rectangle like that. It's got a height. It's got the center. And this right here is the C. So for a rectangle, we learned, and there's charts with all the different formulas back in the book, but for a rectangle, I, which is the moment of inertia for any beam that's a rectangle, is BH cubed over 12. So that's something to remember. And then C is always equal to H over 2. So that from that you get, with that information, you can also get the section modulus, which is S equals I over C, which also equals BH cubed over 12 divided by H over 2, which is the C, equals BH squared over 6. So that's how you can get the S. And from that, you got the flexure formula, which basically says that F equals, there are different variations of it. This one is F equals M over S, or F equals M equals Fs. So you can twist that around with your algebra to solve for whatever variable you need. So in this formula, F is going to equal the stress in the bending, M is going to equal the maximum internal bending moment, and then S is the section modulus. So that's the basics. From that, you can go in to design your beam, which is what we're going to do right now, and y'all are going to help me. So I hope you're paying attention. So let's say that we're going to do a bending analysis on a beam. Let's say that we have, we're going to select a wide flange beam with allowable bending stress of 22 kips per square inch. So we have a beam, first of all. .6. It's 20 feet long. 17.4 kips on the other side. It's got a uniformly distributed load of 1.5 kips per foot. It's also got a concentrated load right here of 12 kips. And that concentrated load is 4 feet from that end and 16 feet from that end. So what do we need to do first? If it wasn't done for you already, in which this case it was, you need to solve for the reactions, and you're going to have to do that in some of your other problems. But here we already have our reactions. We got 24.6 kips there and 17.4 kips there. So the first thing, first thing you always got to do is solve for your reactions. Then you got to solve for your shear and your moment, just like we did a while back. You got to do your shear and moment diagrams. So, the easiest way to do that is to draw it down here. And so what would be the shear diagram for this? What would be the first thing we'll do? Remember? You need to talk to me? Oh, it's my receipt. Hold on one second. Okay, so how do you draw a shear diagram for this? What's the first thing you do? I can't just sit up here and talk to the wall. Well, the first thing that happens going from left to right is you got a force that goes up 24.6 kips. So what do you think you'd do? Right, go up 24.6 kips. And you, whoops, huh? I can't hear you. Just 1 second. Let me undo that line. So you go up 24.6 kips. Then your next action is going to, or sharp action is going to be in line with this, right? But until then, you've got a force, a uniformly distributed load of 1.5 kips per foot. And that's 4 feet. So if it's 1.5 kips per foot, how far down would you go? Is that what 1.5 times 4 is? Right. So you'd slant, when you have a uniformly distributed load, it's a slanted line and goes down about 6 units, whatever that is. That would be 18.6, right? So it lines up with there. Then we got a concentrated load of what, 12 kips? So what will we do? What will we do? Go down 12, that's right. So 18.6 minus 12, we still won't be at 0. It's not lining up right, but that's okay. That would be 6.6. Then the rest of it is uniformly distributed, and it's going to be 16 feet long times 1.5 kips per foot. What's that? What? So we're going to go down 24, but what is 6.6 minus 24? Yeah, you're right, 17.4 minus. Yeah, so we measure that down, whatever it is. We have a slanted line, and we got 17.4, which fortunately is the same as our upward reaction, and we get back to 0. So there's our shear diagram. Not drawn perfectly, but drawn. so, um, so remember that the maximum moment is where? Where does the maximum moment occur? The maximum moment occurs where the shear is 0. Remember that? Maximum, that's a key point. And that's where you need to worry about your design, because that's where the beam will break, if it breaks. So then below the shear diagram, we're going to draw the moment diagram, knowing that our maximum moment is going to be in line with that, right? Because that's where it equals 0. So, and we have to figure out where that is on there. Or do we? So do you remember how to do the moment? Remember, the moment is going to be kind of curved, right? But the high point will be in line with this. So the moment's going to look kind of like that. But we need to figure out what this point is. So, and that's going to be equal to the area of these things. So you got to figure out what your areas are. If that was a clearer picture, it'd be easier. So let's see if we can, we know that this is 4 feet right here, right? Yeah. So there's a square that's going to be 4 feet, or 4 feet by 18.6, right? Yeah. So we got that one, 4 times 18.6. That's going to take care of that area. And we got this one up here. This was 6, right? And we know it's 4 long. So if that's going to be 6 times 4 divided by 2, right? That's the next one. So we got that one. Now we need this little bitty triangle here, which is going to be, I'll blow that up. It's going to be 6.6. Dang, this is hard to write on. That side's going to be 6.6. Then we got to figure out what this little bit here is, how long that is. What? It's 6.6 from here to 0. Remember? Okay. So we just got to figure out the bottom part, this length. Does anybody know how to do that? Without AutoCAD? Well, trying to, if you were doing it, you know, if I was drawing it to scale, I know what it is, but you would just be able to, I mean, I think for the purposes of our exploration, we can scale it, and it would be, this distance here is going to be 11 foot 6 inches. So that's from there to there. So then this little bit here, if you do the math, the whole thing is 20 feet long minus 11 foot 6 minus 4 is going to be what? Anybody know? 20 minus 4 is 16, minus 11 foot 6 is, okay, is that right? It's 20 feet. Not sure why that, how I did that. I'm sorry. Probably would have been better to do this other side. So I think that's what I did. So we know that this is 11 foot 6 because and we know that this is 17.4. So erase all that. You're going to say that 11 foot 6, the area of this space here is going to be 11.5 times 17 over 2, because it's a triangle. What does that equal? 11.5 times 17.4 divided by 2. 100.05. So that's going to be our maximum moment. It's going to be at 100. Rounded down would be 100. So now we solved for the shear and the moment. Now you need to solve for the section modulus. This is if you had to figure all this out yourself, which you should be able to do. There's also charts sometimes that help you find these numbers. So if you want to solve for the section modulus, which is F equals M over S. So we know that M, or that also can be changed to S equals M over F, which is going to be equal, we know that the maximum moment is the 100 times hold on. be 100 times 12 over the 22, which we got, I didn't write it down, but it says in the problem, it said the allowable bending stress was F equals 22. But that information was given to us. So if you add all that out, you're going to get S equals, what's, that'd be 120 over 22. Equals what? Gosh. What does that equal? 1200. What? 54.54. Inches cubed. That's your S. So now you need to look in the chart and you want to select a wide flange beam, looking at the chart, that will allow you to have an S of 54.54. So y'all look in your charts and tell me which one you find. I think it's in chapter 10. There it is. Okay. So we're looking at we want to know the S about the x axis. So we would go down the chart. I'm on page 202. Our section modulus is 54.54. So we need to go down until we find a beam that would support that in the x-axis. Yes, the next one above it. The smallest beam that would support it is what you want. What? What's 56.5? What beam number is that? $1636. 56.5. That would work. Oh, I did forget one thing. If you, they didn't tell you this in the book, but if you want to, beams generally carry about 3% of their weight is 3% of what they carry. So you can multiply this number times 3%, which would be times 1.03. What would that give you? That gives you a margin of error. What would 54 times 1.03 equal? 56 point what? So that changes a little bit, doesn't it? 56.18. So that would be there's multiple answers for this. You could choose a W of 14 by 43, or you could go up and you could still do the W of 16 by 36. You probably have to base it on what kind of space you have to design, what would work better. But you see how that works? So So let's say we chose a W 14 by 43. So what, by that nomenclature, what is the weight of the beam? No. What do we know from that, just a W 14 by 43? What does that mean? It means this is the pounds per foot. So it's 43 pounds per foot. And it's 20 feet long, so how much does that beam weigh? Because we're checking the weight of the beam now. What? 860? Good. Okay, so we want to make sure that this design is still okay. So for the moment of the beam, from our formulas that we already know that are listed in the book, M equals WL squared over 8. Which equals the W, which is the 43 pounds. L is the 20 feet, right? Squared over 8. Somebody figure that out. What? 2150? I don't have that. I have 2145. So it's 43, or 20 times 20 times 43 divided by 8. Is that what y'all got? What'd you get? 4,300? Hold on. It should be 43 times 20 squared, or 20 times 20 times 43 divided by 8. Here's my calculator. Well, this could be on. There it is. It's not going to show me on my calculator. Okay, well, this must have been done wrong. Okay, 2150. I trust you. So I don't know what I did wrong, but okay. So you saw that's the moment is 2145 foot-pounds, or 2.14. I mean 2150 foot-pounds. What? I don't know. Okay, now you need to solve for the S with this weight. We're just checking to make sure we designed this beam right. So S, the section modulus is S equals M over F, which is going to be equal to 2150 over the 22 KSI from way up there, our allowable bending stress. So that equals what? Wait, I did something wrong. 2150. What'd you get, Ariel? Oh, we have to multiply this by, yeah, times 12, right? 2150 or 2.150 times what? Why not? But I want to make this in inches. Okay. Either way, right? Okay. So 2.150, so they're both in kips. Huh? Inches. You did 2.150? I added the decimal there. Because this is just pounds. I'm making it kips. Because this is kips. So 2.150 times 12 divided by 22 is that's better. Thank you, Keith. I'm going to leave it like that. So the total S required for this beam is going to be what we got above here. What was that? 56.18 plus the beam itself plus 1.17. This is total S. What does that equal? 57.35. So now we need to go back to that table and see if that what we sized is still okay after we added the weight of the beam. And that was a 14 by 43. It's okay? Okay. Yes. So it's okay. Yay. Okay. So, I mean, that goes, the book gets very involved with their stuff, in explanations and things. But when you break it down into the simple formulas and you have to go back and look at charts to find the information that you'll need, I think you can do the, you can figure out the questions that they're asking you to do. Let me find where I'm at. It's not break time. Not yet. So, so I put on the canvas what the problems were, but basically it's the problems in the book. I didn't do all of them. I did most of them. But you just need to go through them and kind of match up their examples with what they're asking you to do and figure out if it's the beam is safe or whatever it is they want to know, or what the maximum load is. I want to go over shear a little bit. So when a beam is bending, you know, this is exaggerated, of course. It's like these are the fibers in the beam. There's a lot of shear stress in there, and these are all kind of, you know, sliding past each other when it's bending. Does that make sense to y'all? So there's internal shear, and you have to check for that. So let's go through a problem of that. We're going to have a beam that is 12 feet long. 12 feet long, and it's going to have a uniformly distributed load of 1,400 pounds per foot. Back up. I'm going to go up here where there's more space. First, you got to figure out F. And we were given, I didn't tell you this before, but we were given a beam that's 13 inches, the wood beam, 13 inches by 5 inches, the glulam. So in this situation, the S is going to equal, because it's a rectangular beam, it's going to equal BH squared over 6. So B is 5 and H is 13. So 5 times 13 squared over 6 equals what? What'd you say? Okay, well, we'll round that up to 141. So back down here, that's our F. So back to this formula, we got F equals M over S. So F equals 25,200 over 141 equals 25,200 divided by 141 equals what? Totally different than what I had. What did I do? I'm missing something. 2,140 psi. Mm-hmm. 2,140 psi. Bending stress equals F equals M over S. 25,200 divided by 141. That's 25,200. Oh, we got to multiply it by 12. I didn't write that down. Times 12. Because this is in foot-pounds. So do that. 25,200 times 12 over 141. You get 2144. Okay. And that is less than 2,400. Which I think if you look up the F for the 5 by 13 glue lamb, that's what we're checking against. 13? Huh? Find that chart again. What? Structural lumber. Well, you're right, I don't see it either. Yes, I must have gotten that out of another book. I can't wait till I have a new book. I don't either. But that, technically that, I mean, you would compare it, once you figure all that out, you would compare that F to whatever it is you're sizing, and if it's less, and when this was done, it was less, that's how you would check. Then, I thought it could go on forever here. If you want to check for the shear stress, you have to use the formula F shear stress, which is stress for the shear, which is V, equals 3 over 2 times V over A. And that formula is derived in the book. It tells you how they got it. But the V is the shear and the A is the cross-sectional area. So the V our maximum shear based on our shear diagram before was 8,400, right? I'm not going to flip back to that page. So that's 3 over 2 times 3 over 2 times 8,400 over the area, which is 5 by 13 is what I said, right? Yeah, 5 by 13. So then if you multiply all of that out, you should get what? Yes, times 3 over 2. So VF equals 32. 1 second. Let's work through this a little bit. I'm sorry, I'm missing something again. If you have your checking for your shear, which has to is the 8,400. Got to understand that. So your F sub V equals 3 over 2 times V over A. So then you got the V is 8,400. Huh? BD is the area, space times depth. Yeah. This was done differently. This is 8,400 TF. Oh. What did I do? I must touch something. Ah! I hate this thing. There. Okay. 8,400 psi, and then 5 times 13 is what? Just for my curiosity. What? 65. Okay, so you got 3 times 8,400 is what? 25,200. And then 2 times 65 is what? 130. So then what's 25,200 divided by 130?
193.84.
That's better. Okay. See, that's not right, I don't think. One, 193 point what? So that's 193.84. So if V is 8400 and then F sub V is 194 basically, that's greater than the 175, which is what that beam would hold if you did it, what's the six? Huh? Oh, okay. See, that made me all freak out. Okay. So V equals 8400. Okay. The allowable shear stress is 175, and they got that from the F sub V equals I'm not sure how that was. You would check that with the load or the beam diagram, which we don't have. That's how they figured that out. But so we figured out our F sub V, and then we check it against the diagram, and it should be okay.
That's the actual shearing stress, right?
Yeah.
And then isn't there a more we can check for the maximum?
What?
Isn't there a way we can?
Well, in the nice world, it would be in the chart. So, but what I suggest you do, I've worked through the problems in chapter 12, so you need to read that. I thought this was a simpler explanation, but now I'm not so sure. But read through chapter 12, then do the problems that I put on Canvas, and it's with what I gave you here and then what the chapter gives you, you should be able to figure out the answers. And then you can post any questions or comments on Thursday's discussion. And then I'll also put chapter 13 on there. And then Tuesday we'll answer any other issues we have before we take a test on it. Okay? This class wears me out.
Break time?
Yeah.